Hello and welcome to our first lesson on factors and products, factors and multiples of whole numbers. First, we're going to start a lesson off with some definitions. I know that these are definitions because they're bolded and they have colons. So I'm going to highlight them because I know that these terms are going to be used throughout the lesson that I may have to reference back to or reference when studying. So factor, a whole number, that a value is evenly divisible by. An example of that would be that 4 and 5 are factors of 20. That's just one example. Now we have a product. So we think the result when you multiply, and I know that multiply is specific when talking about a product, so I'm going to underline that, and it's 2 or more numbers. So an example, 18 is the product of 2 multiplied by 9. Now think of multiple. You could probably think of multiples of 2, 2, 4, 6, 8, so on. So how can we put that into a definition? We have the product, and remembering that product means the result of 2 or more numbers when you multiply them. So a product of a number and any natural number. So as it gave an example, 4, 8, 16 are multiples of 2. Prime number, a number that is only divisible by 1 and itself. An example of that be 7. Last definition that we're going to go over right now is a composite number. So that's a number that is divisible by 3 or more factors. And these are not prime. Now we have a chart here. I want you to add 0 onto this 1 to 100 chart, and we're going to look at the prime numbers by circling them, and I'm going to put red underneath that because that's the color I'm going to use for it, and put an X through all the composite numbers from 1 in the hundreds chart below. So when looking at prime numbers, that's what we're going to start with. We want to circle all the prime numbers. We remember that the definition is a number that is only divisible by 1 and itself. So when we're looking at 0, 0 can't be divided by anything, so that's not a prime number. 1 divided by 1, 1 divided by itself, so that can't also be a prime number. So we're going to start at 2. 2 can be divided by 1, and 2 can be divided by 2. There's no other options, so that's a prime number. You do the same process with 3. When we look at 4, 4 can be divided by 2, so therefore it's not a prime number. 5 is only divisible by 1 in itself. 7, and now so on. I'm just going to circle all of the prime numbers from 0 to 100. And these are the numbers that are only divisible by 1 and itself. $79, $83, $89, and $97. So here we have all the prime numbers. Now we're going to look at the composite number. So remembering that a composite number is a number that is divisible by 3 or more factors, and it's not a prime. So we can automatically rule out all the prime numbers. Now when we have to look at divisible by 3 or more factors, we know that 0 and 1 can't be divided by 3 or more factors, but 4 can. And if we know that 4 as an even number, all down this column are all divisible by 3 or more numbers. 6, 8, 9 can be divided by 3, 10 can be divided by 2 and by 5. So we know that all the even numbers are going to be composite numbers. All of the multiples of 5 are going to be composite numbers because they can all be divided by 5. Here's all the even numbers by 6. I missed 2. 33 can be divided by 11. And 93. 18, 20, this whole tens column is all divisible all the even numbers. Now we have a couple left. 21 can be divided by 7. We also have 51, 81, and 91. And 27 can be divided by 3, 11, 87, and our 9s. So as you can see, if it is not a prime number, it is going to be a composite number with the exception of 0 and 1. What about them? So they are neither a prime or a composite. All right, we have another definition here because I see that it's bolded and has a colon, so I'm going to highlight that. And the definition of prime factorization is a number written as the product of its prime factors. So when I look at this definition, I recognize that product is the result of multiplication and that I know that a prime number can only be divisible by 1 and itself, and that factors means it has to be evenly divisible, so with whole numbers. So we broke down that definition a little bit. We're going to go through 2 more definitions before we get into an example of how to write prime factorization. So here we have greatest common factor and least common multiple. You may be familiar with these terms in the acronyms GCF and LCM. Now, greatest common factor, so that's the greatest factor that 2 numbers have in common. Now, least common multiple, we have the least number that is divisible by 2 or more numbers. Okay, let's take a look at this. We have example 1, determine the prime factors of a whole number. Write the prime factorization for 3,300. And we're going to use what's called a factor tree. So here, when we start with our factor tree, we're going to take 3,300. We're going to start at the top of the tree. I want to think of what two numbers can I multiply together to get 3,300. Could be multiple ways of doing a factor tree. This is how I'm going to break mine up. So when I think of 3,300, I think of 10 multiplied by 330. Now, neither of these are prime numbers, so I have to keep going. So I need to now break 10 down, and I know that 10 can be broken down by multiplying 2 and 5. 2 is a prime number, and so is 5. So that's where the end of that tree is going to stop. 330 can keep going, broken down to 33 and 10. 33 into 3 and 11. 10 into 2 and then 5. And these are all prime numbers. So that is the end of the factor tree. Now, how do we write it out as prime factorization? Because part of the definition says it has to be written. So therefore, 3,300 is equal to, we take these prime numbers here that I circled at the end of our factor tree. 2 times 5 times 3 times 11 times 2 times 5. And if you multiplied all those numbers together, you would get 3,300. Now when you write this, we're going to write into simpler forms. We have 2 times 2, so I'm going to put the like numbers beside each other. Times 3 times 5 times 5 times 11. And now I can write these as exponents. 2 to the power of 2 multiplied by 3 multiplied by 5 to the power of 2 multiplied by 11. So here we have the prime factorization of 3,300. Now we can use this method of prime factorization and factor trees to help us find the greatest common factor. So I'm going to give you two options on how you may want to solve for it. The first option, 1, I'm going to use factor trees. So step 1, draw factor trees, and we're going to do this for both numbers. So I'm going to start with 138. Two numbers multiplied to equal 138, 2 and 69. 2 is a prime number, so it's going to stop there. 69 can be multiplied with 3 and 23. Both of those are prime numbers, so it's going to stop there. So when I write out the prime factorization for 138, I have 2 times 3 times 23. Okay, I'm going to stop there, and I'm going to do the factor tree for 198. That can be multiplied with 6 and, 33. Neither of those are prime numbers, so I'm going to keep breaking down. 2 and 3, both are prime numbers. 3 and 11, and circle the prime numbers. So now when I have the prime factorization of 198, 2 times 3 times 3 times 11, which can further be simplified. 2 multiplied by 3 to the power of 2 by 11. Okay, done the first step, and we also did the second step. We write prime factorization. And the third step, the greatest common factor is the common prime numbers multiplied together. So I'm going to look at 138 and 198 and what are the common prime numbers. So the common prime numbers are 2 and 3. Just looking at the number itself, so the greatest common factor is equal to the common primes, which is 2 multiplied by 3. So therefore the greatest common factor is 6. All right, so that was one option on how you may find the greatest common factor. I'm going to give you a second option on how you might do that. So option 2, I am going to take 138 and I want to list all the products that would result in 138. So I know that I'm going to start from the highest possibility. So 6 multiplied by 23. I'm going to link those. I'm working my way down. 3 multiplied by 46. I'm going to link them. And 2 multiplied by 69. These are the options on how to get a product of 138. Now, how can I get a product of 198? 11 multiplied by 18. Gonna link them. 9 multiplied by 22. 6 by 33. 3 by 66. And 2 multiplied with 99. When I compare these two numbers, I see that the common factors are 2, 3, and 6 with both numbers. So therefore, common factors are 2, 3, and 6. And out of those, the greatest common factor is equal to 6. So here we have two options listing out the possibilities to result in the product compared to using factor trees. So you can choose what option you would like to use to solve for the greatest common factor. Now we're going to use those examples on how to solve for the least common multiple. And the least common multiple between 18, 20, and 30. Now, one option that you could use is the fact that we know multiples of 20 and 30 easier than we would come to of 18. So let's list the multiples of 18. So 18, the multiples are 36, 54, 72, 90. Now I'm going to stop at 90 because I know that 90 is a multiple of 30. I think to myself, 90 is not a multiple of 20. I'm going to keep going. 108, 126, 144, 162, 180. And then I'm going to stop at 180 because I know that that's a multiple of 20 and it's also a multiple of 30. So I'm going to stop there. Therefore, the least common multiple is 180. That was one way to solve for it. Another way you might want to solve for it is using factor trees. So I'm going to determine the factor trees for 18. So I'm going to start there. So I know 18 can be multiplied by 2 and 9. 2 is a prime number. 3 and 3. So I'm going to stop there with my factor tree. The 18 is therefore equal to 2 multiplied by 3 to the power of 2. Okay, now we have 20 broken down to 2 and to 10. 2 is a prime number. 10 can be multiplied by 2 and 5. Gotta stop there. Prime factorization of 20 is 2 to the power of 2 multiplied by 5. And now 30. 3 multiplied by 10. 3 is a prime number. 10 can be multiplied by 2 and by 5. Both of them are prime numbers. Therefore, prime factorization of 30 is 2 multiplied by 3 multiplied by 5. Now, how do we determine the least common multiple between those terms? So we want to multiply the largest value multiple of each prime. So I'm going to look in this box here, and I'm going to circle the highest value of each multiple. So I see that the highest value 2 is 2 to the power of 2. The highest value 3 is 3 to the power of 2. And 5 is the same in either question. So now to determine the least common multiple, I need to multiply 3 to the power of 2, multiplied by 2 to the power of 2, multiplied by 5, and that equals 180 as the least common multiple. Now let's move on to example 4. We have 2 word problems. One we're going to use to determine the least common factor, and the greatest common factor and the least common multiple. So for the first example, when I read out this question, what is the side length of the smallest square? When I think square, I think equal sides, that could be tiled with rectangles that measure 16 centimeters by 40 centimeters. And we're assuming that the rectangles cannot be cut. When I read this question, I visualize in my head what that might look like to get a better understanding of what method I might use to solve it. So I hear that what is the small square that could be tiled? So we have a square and it needs to be tiled with tiles that are 16 centimeters by 40 centimeters. So we want to determine this length. And because it's a square, we know that all lengths are equal. So what is that question mark? So I want to find the least common multiple, the smallest possible square that could be used with those tiles. So I'm going to use factor trees. Multiple of 16 and 40. So I'm going to use factor trees. Here's factor tree for 16. That can be multiplied with 4 by 4. Neither of them are prime numbers. 2 and 2, 2, and 2. That was easy. So now we have 16. The prime factorization of that is 2 to the power of 4. Now we have 40, so that's broken down to 4 and 10. Neither of those are prime numbers. 2 and 2, 2 and 5. So the prime factorization of 40 is 2 to the power of 3 multiplied by 5. Now my next step is to find to multiply the largest value multiple of each prime. So between 16 and 40, 2 to the power of 4 is greater than 2 to the power of 3. And 5 is on its own, that's the highest value. So when we find the least common multiple is equal to 2 to the power of 4 multiplied by 5 is equal to 80. And because this was given to us in a word problem, I'm going to answer with the sentence. So the side length of the smallest square is 180 centimeters. Perfect. So now that I can erase these question marks because I have determined that the smallest square would be 180 by 180 centimeters. All right, moving on to example B. When I'm reading this here, I see what is the side length of the largest square that could be used to tile a rectangle that measures 16 by 40. Again, we're assuming that all squares cannot be cut. So I'm going to visualize this. I'm going to look and see that the rectangle itself is 16 centimeters by 40 centimeters, and it wants to determine what is the largest square. So square has equal sides that could be used to tile the inside of it. So in this example, I'm going to be coming up with the greatest common factor between 16 and 40. So now we already did the factor trees for it, so I'm going to write out the prime factorization. So 16 is equal to 2 times 2 times 2 times 2, and 40 is equal to 2 times 2 times 2 times 5. To determine the greatest common factor between those numbers, that is the numbers multiplied together that are common. So the only ones that are common is 2, 2, and 2. So therefore, 2 multiplied by 2 multiplied by 2 is equal to 8. So the greatest common factor is equal to 8 centimeters. How do I put that in the sentence? The largest square has a side length of 8 centimeters. Now, the practice questions that go along with this lesson from your textbook is page 140, questions 3 to 13 and 17. They're linked in your OneNote page for you to practice, along with the answer key to check on those, to practice determining factors, products, and least common multiple and greatest common factor. So take a look at those and review the lesson as needed before we move on to the second lesson. All right.